Howdy! In this mini lecture, we will review the scientific method. The learning objectives of this lesson are: explain what the scientific process is and list the steps in the process, describe and identify the two types of hypotheses, describe the different types of data, identify different types of variables used in the scientific process, explain how the word theory differs in the scientific community compared to the communities external to science. To assist your mastery of variable identification, there is an optional variable identification exercise you may choose to do in order to understand key concepts of the scientific process. Please note that this is not required. The scientific method is a traditional experimental approach or technique for testing ideas with observations. It should not be seen as mysterious or intimidating. Once you understand the steps, you can easily apply the method to answer any question, science-related or not. Scientists and you can use this method to learn how the world works. This simple diagram illustrates the general process. However, this diagram cannot convey the true nature of the scientific method because science is inherently dynamic and creative. Researchers often pursue their work in ways that legitimately vary from this model. For example, a scientist may get to the testing phase of the method only to discover that his experiment doesn't work and needs to be revised. Or, during the testing phase, new information may be revealed that requires the scientist to go back and ask new and different questions instead of the original questions. After a test or experiment, results are evaluated to either reject the hypothesis or fail to reject the hypothesis. Notice that the hypothesis is never proven. This is because it is impossible to test every possible cause or reason for a given observation. If a scientist rejects or disproves his or her hypothesis, then they will usually formulate a new one to replace it and run new or improved experiments. If a scientist fails to reject their hypothesis, this lends support to the hypothesis but does not prove it. Usually, the scientist will formulate new predictions to further test their hypothesis. In this way, the process of conducting science is very much a continual process. But there is more to practicing science than just conducting experiments and following the scientific method. Once results are obtained and evaluated, scientists share the results with the scientific, and sometimes the lay, community by publishing scientific papers. Such papers go through a rigorous peer review process during which scientists not associated with the original scientists publishing the paper, but who are experts in the same field, review the publication for validity as well as sound methodology and analysis. Once the paper is accepted, it is published and circulated in the scientific community. Scientists and scholars make it a practice to stay current on the latest advances in their fields by reading these articles. As it is, there is always something new to learn. There are two types of data, qualitative and quantitative. Qualitative data is descriptive data and generally lacks hard numbers. Jane Goodall's observations of chimpanzees' behavior are a great example of qualitative data. Quantitative data are measured data and consist of recorded measurements, which can be organized and summarized into tables and graphs. A great deal of science is conducted as observational science, like Jane Goodall's observations. This is also called descriptive science. Through this method, information is gathered through observing organisms, systems, materials, processes, or anything else that can be observed. In this method, there is no manipulation of the thing, which is being observed. However, measurements can be taken so there can be both qualitative and quantitative data collected through observational science. This method is used in traditional fields such as astronomy, paleontology, and taxonomy. However, scientists have also begun to explore relatively new branches of science, such as genomics and molecular biology, using observational science. Usually, observational science is required before the second method of conducting science can occur. Once enough information has been gathered through observations, hypothesis-driven science can be pursued to further investigate a subject. Hypothesis-driven science is more targeted and structured, and it involves experiments which can test hypotheses using the scientific method. Notice that the plural of hypothesis is spelled with an SES at the end. Examples of observational science often include biological surveys. The picture here is of a rare and endangered marten found only in Olympic National Forest in Washington State. Volunteers put cameras in the forest to try to determine where the martens were concentrated in hopes of ultimately determining the size of the population in the region. An example of hypothesis-driven science could be any experiment in which variables are manipulated in an environment to better understand a subject being studied. For example, drug trials of new medicines are hypothesis-driven science. In such trials, there is a random sample of individuals who are given varying concentrations of a drug or a placebo. The picture here shows a fall armyworm, which through hypothesis-driven science was discovered to be capable of replicating vaccines within its body. Before moving forward, we need to discuss what a hypothesis is. Hypotheses are simply proposed explanations to well-framed questions. From the hypothesis, a scientist can then go on to make predictions which will be tested by either observation or experimentation. In order for hypotheses to work, however, they must meet two important criteria. They must be testable and they must be potentially falsifiable. For example, rock music is better than country music is not a hypothesis because it is neither testable nor falsifiable. It is an opinion. If technology hasn't been invented to test a hypothesis, then the hypothesis must sit idle until such time that it can be tested. There are two types of hypotheses, the research hypothesis, which is denoted H1, and the null hypothesis, which is denoted H0. The research hypothesis is a prediction causing an observation. The null hypothesis negates the research hypothesis. For example, if you are investigating whether organic or conventional fruits and vegetables were more nutritious, the research hypothesis would be, organic fruits and vegetables are more nutritious than conventional fruits and vegetables, because this is what you observed and what you would test. The null hypothesis would simply be the research hypothesis with not inserted into it. This would be, organic fruits and vegetables are not more nutritious than conventional fruits and vegetables. The simplest way to formulate a null hypothesis is to just add not to the research hypothesis. The reason two types of hypotheses are needed is because when scientists evaluate the data from an experiment, it is the null hypothesis which is either rejected or supported. If the null hypothesis is rejected, it would be considered disproven. In the case of the organic versus conventional fruits and veggies, rejecting the null hypothesis would give support that organic fruits and veggies are in fact more nutritious than conventional fruits and veggies. However, if an experiment fails to reject the null hypothesis, then the null hypothesis is supported, but not proven. In the case of the organic versus conventional fruits and veggies, this would mean that there is not significant evidence to indicate that there is a difference in nutritional value between conventional versus organic fruits and vegetables. A hypothesis is never proven because there could always be some other reason for the observed results. You can't test for everything. In summary, you either reject or fail to reject a null hypothesis. Experiments are defined as contrived situations that test the validity of a prediction or hypothesis. Variables are factors that can change in value under different conditions. Variables can be manipulated or left constant. Independent variables are the variables manipulated by the scientist. Dependent variables are the variables which cannot be changed by the researcher. Dependent variables are what is being measured and influenced by the independent variable. Dependent variables are dependent on the independent variable. For example, if you were comparing cleaning products, you might test OxyClean, Clorox spray, and a generic brand. The brand of cleaning product would be the independent variable because that would be what you manipulated. The dependent variable would be how well each product cleaned a surface. When the cleaning surface has a constant level of dirt and soiling, type of dirt or stain, and amount of time each product was used on the surface. The variables which remain the same for each trial surface cleaned would be considered the controlled variables. These must be held constant, otherwise we will not be able to clearly evaluate and compare each cleaner. Failure to standardize even one of these controlled variables could cause a confounding variable and invalidate the results. Students inexperienced with the scientific method often incorrectly identify dependent and independent variables. Another common source of confusion is the difference between a control and a controlled variable. Recall that there are three types of variables: independent, dependent, and controlled. Controlled variables are items or scenarios that remain constant throughout the experiment. Thus, they may also be called constants. They are meant to establish or refute relationships between dependent and independent variables. When water flows through a sink faucet, the independent variable is how much the tap is opened. Dependent variables are the resulting amount of water flow. Controlled variables would be the faucet and water pressure, as long as they remain unadjusted. Controls are different from controlled variables. A control checks or corrects information obtained in other experiments by removing all variables except the one of interest to the researcher. Controls normally require no manipulation on the part of the research team. If you were testing the effects of an automotive wax, then the control would be the area of the car that had no wax applied to it. The control would then create a stark contrast between treated and non-treated areas on the car. In the case of a drug trial, the placebo, or a sugar pill with no medicine, would be the control. Controlled variables in a drug trial may include how much exercise, food, water, or stress each trial participant receives. The independent variable in the drug trial would be the concentration of the medicine being tested. And finally, the dependent variable would be the measure of effectiveness of the medicine. For example, how fast was a rash healed or how much heart function was restored in response to the medication. In summary, controls are a non-manipulated point of comparison. The experimental group is the group subject to the independent variable. To simplify things, it's best to have only one variable of interest which differs between the control and experimental group. As mentioned before, a key element of science is repeatability. If one scientist conducts an experiment and finds radical results, but other scientists can't repeat it, then that usually calls into question the validity of the original experiment. It's important to publish studies so science can continue advancing. Another common misunderstanding surrounding science is the use of the word theory by scientists. In the world outside science, the word theory is often used to suggest something that could happen or could be occurring. In the lay interpretation of this word, there is rarely any proof, but rather a theory is usually shrouded in speculation. In science, however, a theory is a widely accepted, well-tested explanation of one or more cause and effect relationships. Scientific theories have been validated by a vast amount of research. Scientific theories are broad, consolidate many hypotheses, and are supported by a large body of experimental and observational data. For example, Darwin's theory of evolution by natural selection has been substantiated and validated by thousands of experiments and observations over the course of 150 years. Because of its strong support and explanatory power, evolutionary theory is a central unifying principle of modern biology. Other scientific theories include the theory of relativity and the theory of plate tectonics. That concludes the mini lecture on the scientific method. Please review the weekly outline and complete the activities for this week per the schedule set forth in the outline. The optional variable identification exercise is posted in this week's folder. Feel free to use this to practice identifying independent and dependent variables. This is a key concept and often one missed by students.